All right, so we are presently ESYS 54, and this will be our analog discussion. So let's go ahead and start with diodes. So with diodes is a two-layer P/N junction device. It is drawn this way, your basic diode. And it's called the PN junction because this side is made of P material, and this side is made of N material. And we use diodes in the most fundamental use, basic function. It's going to be blank, blank, two words. And I want you to think of these two words. The two words will be electronic switch. Okay, I just want you to think about it as being an electronic switch. How do you switch? Sometimes it's going to be on, sometimes it's going to be off. How are you going to, you already know with the mechanical switch. So remember, your mechanical switch is set up as here, or it could also be set up as this. Okay, it could be open or it could be closed, yes? Your mechanical switch. So that being said, we want to use our diode to behave this way. Sometimes it's going to be open, sometimes it's going to be closed. How are we going to do that for a diode? And let's see, there's another, yes. So how we can do that is through a technique known as bias. This is a really important word. You want to add this to your journal, bias, B-I-A-S. And bias is a voltage across or a current through a device that establishes its mode of operation. Okay, that's a very important definition. You will see bias come up as a definition, not only for diodes, but you will see bias come up as a definition for transistors as well. But this is correct, and it does apply to both kinds of devices we're going to play with. So bias is a voltage across or a current through a device that establishes its mode of operation. So when we think about a diode has to be controlled with bias so that sometimes it will be an open switch and sometimes it will be a closed switch. And the way that this is done with a PN junction diode is this. If we were to build a circuit like so, and I put a resistor in here, and I go to put a diode here, and then if I draw the same circuit, resistor, and now I point the diode in the opposite direction. Notice there's a slight difference in how I've drawn the diodes. The upper diode is drawn with the apex pointing down. The apex is this part of the triangle, if you will. And the lower diode is drawn with the apex pointing upwards. Have I changed the polarity of my voltage source? No, my voltage source has not changed. So what I happen to have on my voltage source is positive, negative, positive, negative. The long plate is positive and the short plate is negative, if you recall. Now, I have to polarize everything else that's in the schematic. So if I were to mark my polarities, this lead of the resistor is closest to the positive, so this lead must share the same polarity. This lead must be positive, which means the other side is negative. And that starts the pattern of the polarities around this upper circuit. So it starts off positive, negative, and the reason why it's positive is because it's physically attached to the positive side of the source. This side is positive, this side is negative, then this will be positive, then this will be negative, and do I have negative attached back to the negative side of the source? Now look at the lower schematic. The lower schematic, I have this lead of the resistor, it's closest to the source, therefore it must share the same polarity. This lead must be what polarity? Must be positive. This side must be negative, and that establishes its polarity pattern. Positive, negative. Do I again have negative going back to the source? I do. Now, if you recall, in my diagram on the previous page, what part of the symbol of the diode is positive? What part of the symbol of the diode, I don't want to say positive, is P-type versus N-type? And the way you reconcile that, one of the ways, one of the memory tools that students like to use is this. Does this triangle look like a pyramid? Looks like a pyramid on its side, yes? Pyramid starts with what letter? Starts with the letter P. So if you think of this side as being shaped like a pyramid, and it starts with the letter P, that tells you what type of material is on this side of the diode. It is P-type material. This side of the diode, interestingly, has a bar. This bar looks like a negative sign. Yes, does it look like a negative symbol? Negative symbol. And I'll put down resembles negative symbol, whereas this side resembles a pyramid. So this side resembles a pyramid, this side resembles a negative symbol. And the word negative starts with what letter? N. And guess what? What type of material do we call this side? It is called N-type. Now please don't confuse this with polarities. P-type material doesn't mean this is positive. It has no charge. Are we clear on that? There is no charge on this material. N-type, and I should spell this out completely. When I say N material, I should say N-type material. When I say P material, I should say P-type material. So when I'm talking about these types of materials, I'm not inferring that there is any inherent polarity in the material. We'll talk about how P and N materials are formed. They are formed, and we'll talk about that separately. Once they're formed into N and P, then the way that you designate and remember what type of material is on which side of the symbol, this is shaped like a what? Pyramid. Pyramid starts with what letter? Therefore, what material is here? P-type. This bar here is shaped, resembles what symbol? Negative symbol. Negative, the word negative starts with what letter? N. Therefore, this is N-type. Now, there are official names given to each side of these diodes, and the official names that are given are here. This is called the anode, okay, and this is called the cathode. And another way to help you, another memory tool that can help you remember this is take a look at the letter A for anode. Does the letter A for anode have a pyramid in it? Okay. Does the letter A for anode have a period in the symbol, in the letter, yes? So understand that this pyramid for this letter A is associated with the portion of the diode that resembles a pyramid. That will help you remember this side of the diode is called the what? Anode. The other side is called cathode. Okay, so these are the names associated around what's happening with all of this. Now, check this out. I have now applied something called bias. And bias is, as I've said, a voltage across or a current through a device that establishes a mode of operation. Let's take a look and see what polarities have been attached to which side of the diode. I happen to, is this the pyramid side of the diode? Yes. So what material is on this side? N-type or P-type? This is P-type material, yes? And how about over here? Over here we have what type of material? This is N-type. N-type. And the same thing here. Over here, this is what type of material? That little bar designates this is N-type. And this triangle shaped like a pyramid tells you what type of material here? P-type. So far, so good. Now, what you have by virtue of the polarities presented to the diode this way is a certain type of what? Bias. And the bias here has a special name. This is called forward bias. This guy here is called reverse bias. Okay? You have forward bias and reverse bias. Now let me explain to you what happens in forward bias. In forward bias, this guy at this moment will behave like a closed switch. Okay? It will behave like so. So it will behave like closed switch. And when it's a closed switch, can current flow, yes or no? Yes. Current can flow. In this particular instance, in reverse bias, something else happens. What happens is the voltage source remains here. I still have a resistor here. But here, it behaves like an open switch. So, behaves like open switch. Okay, and as an open switch, can any electricity flow, yes or no? No. So it behaves like an open switch when it's biased how? In reverse. It behaves like a closed switch when it's biased how? Forward. And let's look a little more closely at the polarity on these types of material. And here's the keys to the kingdom. The keys to the kingdom are right here. Let me get my yellow highlighter. Highlight some of this. How much of this is familiar to you already? How much of this you've just gone in detail already? Yes, this is review for you. Is this a review for you as well?
Not really. Just review as far as the current and
Okay.
and then we go over diode.
Yes. This is a little more, this is an advanced discussion. So some of this may be review, some of this may be new. So here we go. This is called forward bias because what polarity is being presented to my P-type material? What polarity here? To what type of material? The word positive starts with what letter? And the material starts with what letter? So when I have positive to P, I have an opportunity for forward bias. Take a look at the other side of the diode. I have what polarity here? Negative. Negative is being presented to what type of material? N-type. The word negative starts with what letter? And the word N-type, N, starts with what letter? N. So when I have negative to N, positive to P, this is called forward bias. When I have forward bias, this will behave like a closed switch. Now take a look down the lower diagram. On the lower diagram, I have what polarity at the top of this diode? Positive. But the positive is being presented to what type of material? So I have positive to N, and I have negative to P. So I don't have N to N, P to P, do I? So this is called what type of bias? Reverse bias. Very important you understand that difference. Okay? Very, very important you understand what's that difference. And on a microscopic level, what's happening in the diode junction is this. And I'm going to draw 3 illustrations of a diode body, if you will. I'm going to have a normal diode, normal PN junction diode, and then I will have one that is forward biased. I'm going to abbreviate. And I'm going to have one that's reverse biased. Now, what I'm going to illustrate in this particular drawing is my junction between the P and the N materials. So it doesn't matter which is where, but let's say here and here. So I will have P material here, I will have N material here. And what I have in between, this in-between area is called the depletion zone. Depletion zone. And it has no current carriers. So in other words, the electrons don't normally go through there, okay? It just has none. Now something's got to happen in order to switch this guy on in order to conduct. So what happens is this. I still will have P and N material. I still will have P and N material here. But when this guy's forward biased, my depletion zone narrows. Depletion zone narrows. So when it narrows, this will facilitate easier current flow. There's nothing impeding the current flow. It can narrow to the point of nothing. It acts like a barrier normally. Now, when I reverse bias this, watch what happens. When I reverse bias this, the depletion zone widens. Depletion zone, here you go. It widens. And because it widens, all of this acts like a barrier. Physically, it acts like a barrier. Because it already has no current carriers, since it has no, what are current carriers? Current carriers are your electrons, your holes. It has none of those. And so by reverse biasing this will cause the depletion zone to widen, and the size of the barrier increases. And that's why in the reverse bias, this is behaving like an open switch. No electrons are going to go through this. In the forward bias, you will have this guy behaving like this. It will behave as if it were a closed switch, okay? So here you have closed switch. And here you have your open switch. So this is what happens with a diode when you forward bias, when you reverse bias. The depletion zone will change its width accordingly, and it will either help facilitate current flow through it in the forward bias, or it will impede current flow through it by virtue of reverse bias, okay? So this is what happens microscopically inside a PN junction diode. Are we good with this so far? All right. Now, when, and this is called a PN junction because one side is P, one side is N. Now, enter the transistor that we're about to play with. The transistor that we're about to play with is one of two. You have an NPN or a PNP. And we will call this a BJT BJT. And BJT stands for Bipolar Junction Transistor. Okay? And I could abbreviate this as, transistor could be abbreviated as ESYS-TOR. Okay? That's a valid abbreviation for transistor. So I can have two types of BJTs. One would look like this. The other one would look like this. And I would have here and here and here and here. And I would have a junction here. I would have a junction here, a junction here, and a junction here. So this would be N material, P material, N material, or I could have P, N, and P materials. I will have a wire here, I will have a wire here, I will have a wire there, a wire here, a wire there, and a wire there. So instead of two wires on a diode, on a transistor, you're going to have three wires. And these are configured to be either NPN or PNP. And there happens to be, instead of just one junction between them, because we're sandwiching three layers together, we now have two PN junctions, okay? There and there. There's two junctions in here now. So we have to be careful how we bias this thing in order to have this work. So what I want you to think about here is this. So far, this looks very symmetrical. So far, it looks like the top lead or the bottom lead won't make any difference. They may or may not. I will show you a schematic diagram that, yes, will make a difference. So let me show you what a schematic diagram could look like for this guy. It would look like this. I would have a wire. I would have one coming at this number of degrees. This will come up at an angle, and this will come out at an angle, like so. And then I will have a vertical here, and I will have a vertical here. So far, does this look very symmetrical? I have a horizontal bar, a vertical line, a diagonal, and then a vertical at the top and a vertical at the bottom. So far, so good? Okay, good, okay. I'm going to do the same on this side. Here, horizontal, vertical bar, diagonal, vertical, and vertical, yes? So far, does that look identical to the first one that I drew? Completely symmetrical, yes? Now, watch this particular point. This is very important. This will help you differentiate what's going on in the BJT. I'm going to draw an arrow that points to this particular wire. So it's an arrow that points away from the vertical bar towards the vertical bar that's hanging down. On the other one, I'm going to draw a triangle right here. And the triangle here, in this case, is drawn on this, pointing into the transistor. So this one's pointing away from the transistor, this one's pointing into the transistor. And there's two things that I want to state for you that'll help you identify the leads of your transistor diagram. The arrow always, do that in red, the arrow always points to N-type material. Number one. And number two, the arrow is always always S, in the emitter lead. So copy those two statements down, and then we'll decipher this drawing here in a moment. So two profound statements. Number one, the arrow always points to what type of material? And it's always going to be on what lead? The emitter lead. So it tells you in this diagram, you have what material here? This is N-type material. And the wire that this is on, this is called emitter. The middle lead of these diagrams will always be the base. So this is base, this is base, this is base, and this is base. Right here is base. So the arrow in this case is pointing to N-type material, and it's telling you N material is in the emitter. If N material is in the emitter, that's this picture here, because you have, this is an outside lead. This will be emitter. This is called the emitter lead. The middle lead will always be the base, and then the leftover lead is called collector. Two L's. Collector. So this will be my collector. And if you look at this illustration, this construction of the BJT, this side we said was called an NPN, yes? So I have N on my outside leads, and what's sandwiched in the middle between my N material is P material attached to what lead? The base. So look at this very carefully. That means to tell us we have N material here. On the other outside lead, we have N material, and sandwiched in the middle will be P material. So this is the schematic symbol for an NPN transistor, and specifically, this is N-type material on the emitter because the arrow is pointing directly to it, and the arrow is always on what lead? Emitter lead. So this tells you this is emitter, the middle lead is base, so what's left over is collector. Let's examine what's happening over here. What's happening over here is, again, the arrow points to N-type material. So it's pointing where? It's pointing towards the base. It's telling us N material is in the base. So I have N material here, there's my base, and here's my N material. And this tells you, the arrow tells you which lead is the emitter. So because it's on this lower wire, this one happens to be the emitter. What do you call the remaining lead of the transistor? Collector. So collector exists up there. So this is emitter, and this is collector. Are we good with this explanation of NPN BJT so far? Because I'm going to give you some quiz questions as a thought, okay? Here's a quiz question. I'm going to do this. I'm going to do this, 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 and I'm going to put an arrow here, and I want A, B, C. So tell me A equals, B equals, C equals, and I'm looking for two things. I'm looking for the name of lead, and I'm looking for type of material. So given this illustration, I'm looking for 6 answers. A is what name of the lead, B is what name of the lead, C is what name of the lead, type of material for A, type of material for B, type of material for C. So, Christian? A is the collector, and Carlos?
A
A is the emitter. Okay, so right away we have a disagreement, huh?
Actually, this is the arrow would be on that one. So according to this, according to
whoops.
the arrow is always the emitter lead.
Yeah, according to this, the arrow is always on the emitter lead, and the arrow always points to N-type material, yeah? So remembering these two sentences, if I were to look at this, so go ahead. Christian, what do you think? A would be? A is the emitter? Carlos? Okay, all right, we agree, emitter. And what is B? B is base, Carlos? Base. C is? Collector. Okay, I didn't mean for B to match with B. That I should have labeled them 1, 2, 3. Okay, all right. How about the type of material? The emitter has what type of material? P-type material. What do you think, Christian? Is it P material in the
N-type.
for A? Look at your notes. The arrow
points to the N material.
And which way is it pointing? Oh, it's pointing to B. So what is A? What type of material is A? Ah, you're right. It's P-type here. Because the arrow points to N material, it tells you you have N material where? On the base. So if one of my outside leads is P material, then how about the other outside lead? Must also be what? So what kind of a transistor is this? Exactly. This is defined as a PNP BJT. Are we good with this little quiz? I'm going to give you another one. Are you ready? Cool. All right, I'm going to label this 1, 2, 3. Dunk, dunk. Same idea. I want the name of the lead and want the type of material that we're going to find. And now I'm calling these 1, 2, and 3. So, Carlos, how about give me one of them? What do you think? Where would you start? Lead number 1 is the base. Why do you call lead number 1 the base? The base is always in the middle. Okay, Christian, would you agree with number 1 is the base?
Yes.
Okay, good. Okay, now, Christian, give me another piece of the puzzle.
Arrows pointing for the N material. So then number 3 would be the N-type.
Number 3 would be N-type.
And it will also be the emitter.
And will also be the emitter. Carlos? Okay, you follow? Yeah, it points to N material, clearly, and it's always attached to the emitter lead. So 3 is N-type and the emitter. So far, we are in agreement, yes? Okay, so so back to you, Carlos. What else would you say? Number 2 is collector. There's nothing else to say. Okay, yes. It's what? It would be P material in the collector for number 2. Christian, do you agree that this should be P material here in the collector? This is collector over here. So both of you have agreed that this is P material, yes? Is the collector in one of the outside leads? Remember, the base is in the middle.
Yeah, collector number 2 is the one outside.
Yeah, number 2 is clearly one of the outside leads. So is this expected to be P material? Yes? You both say yes again. You are both incorrect. Again, if we look at the BJT, remember, it's either going to be NPN or it's going to be PNP. If one of my outside leads is an N, then the other outside lead must also be N. If one of my outside leads is P, then the other outside lead must also be P. Because what's sandwiched in between is the odd material. So in an NPN, it must be N, P for base, N for the other outside lead. In the PNP BJT, it must be P on the outside lead, N in the middle, P on the other outside lead. So in this particular illustration, number 2, isn't that an outside lead? Because you agree, number 1 is the base. We have no disagreement, number 1 is the base. You've already defined number 3 as being the emitter because the arrow points and the arrow's in the emitter lead. Isn't the emitter one of your outside leads? So if this is one of your outside leads, then your base must be the opposite material, which means your collector must be the same as the emitter. It should not be P material here. You follow? Okay, so since these are your outside leads, collector must be what material? Must be N-type. Yes, gentlemen. And then the base is P-type. Now you notice I wrote the numbers out of sequence, so you're not going to see NPN or PNP. You actually need to understand that we're not going to see sequencing in here, but if we do write this in the form of collector, base, and emitter, if we do write it in that order, then base is P, collector is N, and emitter is also N. This then tells you what type of transistor is this one? NPN. But here I numbered things to be purposely out of sequence, because I want you to understand the inner workings of this transistor and how to call out the layers. That's really, really important, okay? Okay, so that having been said, let me give you one more to do, just for giggles and laughs. Here you go. And I'm going to do this one this way. Oops. W, X, Y. Ooh, I got 2 X's in here. That's no good. W, X, Y. Okay. And I'm going to do this guy, I don't know, here. All right, so now I want a X, W, Y. I am looking for name, and I'm looking for type. Okay, gentlemen, we'll start with Christian. Name me one lead. X is going to be the base because it's in the middle. Okay, I will go for that. Base. Are we okay with that, Carlos? Okay, okay. What else do you...
N material because the arrow's pointing.
Oh, and it's N material because the arrow's pointing to it. Oh, okay, so we've identified this as base, and it's N-type material. Good job. Okay, Carlos? Which one's the emitter?
W.
Oh, W is the emitter. Why is W the emitter? The arrow is on that wire. Okay, good. And the type must be P material. Why would it be P material?
Because the opposite of the base.
Okay, because the base will always be opposite. Okay, so we will have P. Okay, Christian, back to you.
Y will have to be the collector.
Y will be collector.
Will also be P-type, the outside lead.
Because, and this will be what type of material again?
P-type,
It will be P-type. And why will this be P-type material?
the other outside lead.
Because it's the other outside lead, yeah? N's in the middle, because that's the base, and the arrow points to N material, so it tells you N material is in the base. Outside lead is P material here. This is emitter, because it has the wire with the arrow in it. This is collector, leftover name, and yes, it must be P material because it is outside. Now that doesn't say NPN or PNP, but if you look at the drawing, you read from the outside, PNP, yes? So this is a PNP BJT. Are we clear on how we identify our transistors? So far, so good? Okay, so what you're going to do is, let's see, did he sign you out for lab equipment? Not yet?
Not
So
yet.
I'm going to put this on pause because we're going to start the first. All right, BJT testing with DMM. So when you go to do your BJT testing with Digital Multimeter, you're going to be using use DMM with diode check function. And we'll talk about that on your digital multimeter. On your digital multimeter, when we go to turn the guy on, and we can see this, notice that there is a diode symbol here, also where you measure ohms, yeah? And so we will switch this over to this position. We will get our leads out, and let me talk to you about these leads. I would recommend you pull these out very carefully from your kits, and we don't want the pointy probes. We want the ones with the hooks. So I recommend, do we have hooks? You don't have little hooks on yours? Okay, alligators will work, but hooks work better. You don't have any hooks on yours?
I have hooks.
You have hooks? Oh, I have a defective set. I don't have hooks. I will go ahead and put this on pause. All right, so what we're doing is using a digital multimeter, and the multimeter has to be set in the diode check mode. You want to make sure that your probes are set up black for common and red into the omega port. And we're going to use the little mini hooks. Now, what we're going to be testing this evening will be your transistors. And the transistors that you are receiving are of two types. One is the 3904, and one is the 3906. And 3904, 3906, as you go to look at the device itself, I'm going to hold this as high up to the camera as possible. I'm going to try to focus right onto here if possible. Where's my lens? There's my lens. I'll try to focus right onto here, if that's possible. Ooh, wow, that's pretty good. I can see that. It's focusing on my gloves. Hold it up to the light the right way. It's a 3904. Look at that. You see the markings? 3904. Cool. And so you're reading the flat portion of the package of the transistor. And that flat portion of the transistor has to be facing you when you're looking at these leads, and you identify these leads from left to right as pins 1, 2, and 3, okay? So I'm going to, on this piece of paper, identify, here's my transistor, here's the top, here's the sides, and I have pin, pin, and pin, yes? And I'm going to label this as pin 1, pin 2, and pin 3. And I'm going to set this guy right out here. So what we're going to do is we're going to make measurements using the diode check function on 2 pins at a time. Now what the diode check function does, the diode check function will send a small current. It will send a small current through these leads, and we will be able to measure a very small amount of voltage that will appear between the wires only when we forward bias a junction. Did you hear that? Only when a junction is forward biased will you be able to get a reading. So I'm going to move this aside for just a moment and talk to you about biasing your transistor, because we already talked about biasing a diode. Let's talk about biasing a transistor. Okay, so here, we happen to have a base lead. We happen to have, and that might not necessarily match up with this, but we'll find out. Let's call this a emitter lead on one side, and let's call this a collector lead on the other side. So your middle lead is always going to be base, and one of the outside leads is going to be emitter, the other outside lead is going to be collector. So far, so good? When you go look up the data sheet for a 3904, so this is a 2N3904, you come to find out that the 3904 is an NPN BJT. So that means we're going to have N material here, P material here, N material here. So guess what? If I were to hook up, because this has a small current, small voltage, if I were to hook up my leads this way, if I were to hook up my red lead to the N material and my black lead to the P material, now red lead, positive, if you will, positive to N material, black lead, negative to P material, how am I biasing this junction that is sitting between this junction right here? There's a PN junction right there. That is a PN junction right there. And it has a depletion zone, DZ, depletion zone between these. So this portion here, the P and N, that is a diode by itself. Your transistor is actually two diodes sandwiched together. Because on one side, on this side, I have a PN diode, but on this side, I have another PN diode. So it's kind of like putting two diodes together to form a transistor. If I go to hook up my leads this way, negative lead of my voltage source to P material, positive lead to N material, how am I biasing that junction, Christian? Reverse bias. When I reverse bias a PN junction, how will that depletion zone change? Will it widen or will it narrow? It will widen. When it widens, will it make it easy for current to flow or will it make it hard for current to flow? It will make it hard for current to flow. In other words, will there be a little resistance or will there be a lot of resistance? A lot of resistance. So when I go to reverse bias a PN junction, I should see lots of ohms, yes? All right. How about if I switch these leads around? Suppose for a moment I go and hook up the black lead here to N material, hook up the red lead to P material. So the red lead is the positive side of the source, hooked up the P material. The black lead is the negative side of my diode check, which is the voltage source, to N material. How am I biasing this junction now? Forward bias. Do I expect to see very small depletion zone? Do I expect to see very small ohms here? Yes, I expect to see very small ohms here. Cool. So this is what happens. This is what we're doing with a transistor testing using a digital multimeter, is we're going to test various combinations of 1 to 2, 1 to 3, 2 to 2, 2 to 3, 2 to 1. We're going to test various combinations. And we have a nice worksheet that will allow you to tally your information. So if you take a look at your worksheet is right here. There's your worksheet. And you are asked to measure with the red lead on pin 1 and the black lead on pin 2 a specific meter reading. Now sometimes, if you look at these, it may be easier if you gently pull these leads apart so it's like this. And let's go ahead and do this. Remember, pins 1, 2, 3, the way we've laid it out in our drawing. This is how we lay out. So we're going to take our red and we're going to hook up to pin 1. Is my red hooked up to pin 1 right now? And is my black going to be hooked up to pin 2? Like so. Do I have that connection? Do you have that connection? And when you do, what does your multimeter show you in this particular combination? How many ohms for the diode check? OL means out of limit, okay? So out of range. So if we have infinite ohms here, yes? So infinite ohms, you want to record that value in your notes. So in this particular case, my 1-2 combination is going to be infinite ohms, right there. Infinity ohms. So guess what? What combination would give you infinity ohms? You could have infinity if you reverse bias this junction. So in other words, if I were to put my positive lead to N and my negative lead to P, would I reverse bias this junction? Would the depletion zone be wide? Would I have lots of ohms? So maybe this is one of my a reverse bias of P-on junction. We don't know yet. We have to collect the rest of the data on here to decipher what's happening, okay? So let's go ahead now, let's do a 1-3 combination. So here's 1, okay? And here's 3. So I now have a 1-3 combination, red on 1, black on 3. And this one is reading, on my instance, I'm reading out of limit. Yes, so I'm reading infinite. What are you reading there, Christian? Yeah, Carlos, also infinity? Okay, I'm going to write that down. Infinity ohms, like so. Then we're going to do a 2-1 combination. So it means I'm going to put red on 2 and black on 1. Yes? Switch these guys around. So I now have black, red on 2, and black on 1. Is that what you have? And what is it do you measure? I measure infinite also. You measure infinite? Okay. So we have infinite again. Infinite ohms, right there. Now we're going to do a 2-3 combination, yes? So my red is already on 2. So now I'm going to switch the black over to this side to measure 3. So am I measuring a 2-3 combination now? And my 2-3 combination is showing me some information, yes? How many ohms do I have in this particular case? Do you see ohms, yes or no?
Yes.
Okay. And Christian, how many ohms do you see?
37.4.
Okay, yes, changing. And how many do you have, Carlos?
Around 27 mega ohms.
Okay, and I'm going to write down as steady a number as I can see here. So it looks like 29 point, and you got to average because this is going to change. But hold steady, I'm going to call this 29.88, okay? Because if I stare at it long enough, my eyes will go crazy. So 29.88 mega. Right there, so far so good. Okay, the next combination will be a 3-1. So I'm going to put my red on 3, and I'm going to put my black on 1.
Mine's all putting switch over to out of limit, but even though we were measuring up there for 23.
Mm-hmm.
And then all of a sudden,
For your 2-3 combination, now it's out of limit. Try a different scale. Scale. Range. Try a different range, I'm sorry. Range. Are you still on 2-3?
Yeah.
And it doesn't show anything?
It was that first one, then also.
I'll come over and take a look at that. And Carlos, what do you have for 3 and 1?
Infinite.
Okay. Christian, can you go ahead and measure 3-1? We'll come back to your 2-3 combination in a moment. Mine also shows for 3-1, out of limit. Okay. So that's infinity. Now let's try a 3-2. So the red is on 3. I'm going to move the black to 2. 3 and 2. And am I going to get something here? Am I going to get anything here? Okay, what do you have between 3 and 2? Okay, and Carlos? Infinite. All right, let's go back to 2-3 combination. So here's 2, and here is 3. 2-3 combination. Here we go. Now make sure, are you on the diode check function? Does it show diode on the top? Yeah. Okay, yeah, be sure you set this so that we have it on the diode function, okay? So in this particular instance, we're measuring 0.662 volts. So let me change this to 0.662 volts. And so Christian, what do you have for 2-3 combination in the with the diode check function showing?
Now it barely came back on, so I got 38.6.
No, we need you to press the select button until there. That's the diode check. You see the diode symbol at the top of the symbol? Okay. What is your voltage?
0.636.
Okay, that's what you need to record for pins 2-3, yes? And Carlos? Good. Okay, record that. And then so now, to make sure, let's go ahead and do a 2-1 combination. Could you do a 2-1 combination, please? A 2-1 combination using your diode check. Forgive me, I think even on my own, I didn't have the diode check function on. So with the diode check function on, are we red to 2 and black to 1? Okay, and I get 0.673 volts. Okay, and what reading do you get, Chris? Carlos? Okay. All right, record that value because each of your values is going to be slightly different. So here's the thing. This is how you interpret your results. The way you interpret, be sure to take your transistor very carefully, put it back into your lid or container and set it aside for the time being. Let's turn off our multimeter so we don't waste the battery. And now let's examine the data that we've collected so far and see if we can summarize what's happening here. I will tell you that when you have 2 readings that show you some numbers and the other 4 readings that show you infinity, your measurement is valid. Okay, everything is working properly. Now, you should only show 2 values of readings and the other ones should always be infinity. Let me show you why. If you take a look at this illustration that I have, if I go to use this as red and I go to use this as black, if I'm on my outside pins, if I do here and here, is my black attached to N material? Is my red attached to N material? Am I trying to measure across 2 junctions? Okay, it's hard enough to measure 1 junction because I can forward or reverse bias 1 junction, but I can't measure across 2 junctions. That's definitely going to be infinity. Okay, so whenever I'm on my outside pins, oh yes, let me let him in. Let me pause the recording for just a moment. Here we go. If we take a look at this, if I'm measuring my outside pins, it doesn't matter what polarity I put on my outside pins will always give me always, always, always going to give me infinity, infinity. Take a look at your data. Which pair of pins are infinity, infinity? Which pair of pins are infinity? There's 4 are infinity, but which pair of pins are infinity, infinity? So you have a 1, 2. Do you have a 2, 1? A 1, 2 is infinity. Do you have a 2, 1 that is infinity? No. So the 1, 2 and the 2, 1, one will give you infinity, one won't. Which combination does a 1, 3 and a 3, 1? Hey, look at this. We found one. 1, 3 and 3, 1. Both of these give you infinity, yes? When you find that combination, a 1, 3 or 3, 1, that gives you infinity, it tells you your outside pins are 1 and 3. It tells you one of these is a pin 1 and one of these is a pin 3. One of these is emitter, one of these is collector. You don't know which one yet, but it tells you immediately those are your outside pins because you got infinity, infinity. Take a look at the remaining 2. We said that a 1, 3 combination. So we said that this one here, the 1, 3 and the 3, 1, both gave you infinity, infinity. They are outside pins. Will the other infinity, infinities be opposite pins? In other words, this is a 1, 2. This is a 2, 3. They're not the same set of pins, are they? This is a 1, 2 giving you infinity. This is a 2, 3. So there's 3 separate pins here. So this combination are not your outside pins. Only this row and this row are your outside pins. So we've identified the outside pins as being 1 and 3 because they give you infinity and infinity. Now, you need to identify the missing pin of that set. Which pin is missing out of that combination? Number 2. 2 is your common pin. 2, in this particular case, the common pin is the base. It tells you number 2 is clearly base. Okay? Because that's a 1, 3 combination. 3, 1 gave you infinity, infinity. The only number missing out of these is a 2. So 2 must be your middle pin. It must be your base. Now what you need to determine, look at this picture. Now what you need to determine is pin 1 emitter or is pin 1 collector. We don't know that yet. Okay, we don't know if this part up here jives with what's going on down here. We need to determine whether this is emitter or whether this is base. Is this emitter or this is base? When we forward bias, the higher value number you measure will be your base emitter junction. That's the rule. Which of the 2 measured values, which of these 2 measured values is going to be the higher of the 2 values? Okay, and if you take a look at the values that are measured, you see these 2 that are measured here? Your numbers are very different than mine, but clearly you have measurements here. Take a look at the common pin. The common pin is pin 2, is it not? The common pin here, where you have measurements, is going to be the base. That's another confirmation that base is number 2, because it appears here. Now what you have to differentiate is your outside pins, 1 and 3, which one is emitter and which one is collector. And the one that has the higher measurement is the emitter. So if you take a look at this, it turns out on my paper, it's the 3rd row. How about on your paper? Is it the 3rd row on your paper also, Carlos, that has the higher value? Then that tells you number 2 is clearly the base, then pin 1 must be the emitter. Did you follow that? This one must be emitter. Okay? Must be the emitter. And so if you've identified this, that pin 1 must be the emitter, it tells you pin 1 is emitter, pin 2 is the base, pin 3 is the leftover, is the collector, yes? Are we happy with how that fills in? Now you need to determine the type of material that's here. Is it NPN or is it PNP? We don't know. But your measurements will tell you, because if you have forward bias, you have one of these two situations. You are either going to have, let's see, where's that picture that I drew? You are either going to have one of these two. We don't know which. So when we have, we identified collector as being pin number 3, yes? Emitter as being pin 1. So I'm going to go ahead and mark number 1 here, mark number 1 here. Number 2 is the base. Number 2 is the base. And number 3 is the collector. Number 3 is there. Number 3 is there. You need to determine from this data, do I have an PNP or do I have an NPN? And the way that you can tell is in your forward bias portion of your data. Forward biasing occurs in row 2 and row 3 because you've got some values. So take a look at where the red pin or where the red probe is connected to. The red probe is connected to pin 2. So here's my red probe, and the black probe is connected to pin 1. So if I do this, red probe connected to pin 2, right there, and the black probe connected to pin 1. Is this going to give me forward bias? I have black to P, red to N. Is that going to give me some kind of a number here that could be forward biased? No. So it doesn't look like it's going to be a PNP. Let's take a look over here. Now I'm going to put my black probe on pin 1, red probe on pin 2. Why? Because my table said red probe on pin 2, black probe on pin 1, and I have a value. Is this going to give me forward bias? Black, so black negative to N type, red positive to P type. Am I going to forward bias that junction there? And if I forward bias that junction, will I get a reading? Yes. So is it very likely this is going to be an NPN? It's clearly not going to be a PNP, because if I have my black probe, red probe on pin 2, black probe on pin 1, I have forward bias, I have a number. Is this possibly forward bias? No, this is completely reverse bias. Red to N, black to P. That's reverse bias. That will not give me any kind of a value. That will give me infinity. And I clearly don't have infinity here. So it must be this. It must be an NPN. Can we validate that with the row 4 measurements? Row 4 says red is on 2. There's red is on 2. And black is where? Black is on pin 3. So now I'm going to put black on pin 3. That's pin 3. We identified as collector. Red identified as base on pin 2. Do I have positive to P material, negative to N material? Am I forward biasing or reverse biasing this junction? This one here. Forward bias. Because if I were reverse biasing, what would be my measured value? If I was reverse biasing, this would be infinity. But I have a measurement. So this tells me I am forward biasing this junction. That tells me pin 2 is clearly the base, and one of these is collector and one of these is emitter. And which one is a collector, which one is emitter? We said that the row that has the higher value identifies that pin as being the emitter. Therefore, in this case, pin 1 must be emitter. Just by testing this simple little transistor, we have verified this guy is one of those, okay? This transistor is one of those. Are we good with that? All right. You have another transistor. Let's pull out a 3906. So pull out your 3906 and repeat these steps and see if you could determine if it's the same, if it's different, how is it different, what leads are which. So look at that very carefully. Hold it up to the light. You can see the markings as they reflect off the flat spot, and you will see a 3906. Can you identify 3906 on the body of that transistor, Christian?
Yeah.
Okay, good. Okay, all right. So from left to right will be pins 1, 2, 3. Okay, that will be our standard, 1, 2, 3. Now go ahead and fill in these measurements. Oh, we didn't fill in this table, did we? Oh, we almost finished. Here. So what material was emitter?
That was N-type.
That was N-type material. The base was what type of material? P-type. And this is N-type. Okay, let's go ahead and do the data for the next one. I'll go ahead and put this on pause. If we go to do the analysis, again, we look at our data. And if we look at our data closely, we said that the two rows that give us values tell us that we have forward biasing. And if we look at this information on these two rows, which pin number was common between these two rows? Pin 2 was common, so pin 2 must be the base. The leftover pins, 1 and 3, one of them is collector, one of them is emitter. We said that the higher value row tells you which pin is the emitter. So if 2 is the base and this is the higher value row, then pin 1 must be the emitter. So pin 1 is the emitter. That tells you pin 3 is the collector. So far, so good? Now, can you determine what type of material is existing where in this particular exercise? And how would you be able to validate that this is going to be PNP?
Because the arrow will be on the emitter.
The arrow will be on the emitter, yes.
It'll be pointing towards the base, which will be the N-type.
But how do we verify from here that we have N-type material in the base?
Well, doesn't the arrow always point towards the N material?
The arrow, yes, the arrow is, you're correct. The arrow always points to N-type material, but how do we know we have N-type material in the base? What aspect of this data tells you you have N material in the base? You're almost there. You're almost there. Here's the keys to the kingdom. It tells you, right? Red lead is on pin 1, yeah? Black lead is on pin 2, yeah? So when you have this arrangement, it gives you forward bias. This tells you that the positive lead must be on P material, yeah? So this tells you pin 1 must be P material. The data on the row tells you you have P material on the emitter, which tells you you have what material on the base? N material on the base. So by reading how the leads go to attach to these pins, that tells you P materials in the emitter, N materials in the base. Therefore, now you know which way to draw the arrow. Okay, you were correct. It always points to N-type material. But how do we know that we had N-type material here at the base? The way you know is by looking at the forward biasing that occurs here. Forward bias occurs when the black lead is on pin 2 and the red lead is on pin 1. That tells you pin 2 must be N-type material. The base must be N-type material. Tells you pin 1 must be P-type material because you have forward biasing. That's how you conclusively tell. Okay, because I can give you another transistor that has no numeric relationship to these whatsoever, and you have to do the same test, the 1, 2, 3 test, and you need to decipher what it is. That'll be part of next week's practical quiz. You will do that and demonstrate that. Okay.
Is a rectifier a type of transistor?
Is a rectifier a type of transistor? No, rectifier is a diode. The PN junction device is the two-layer device. Your transistors are three-layer devices. So we have different kinds of three-layer devices. The BJT is the most basic three-layer device. There are also four-layer devices. Your thyristors, your SCRs, silicon controlled rectifiers are four-layer devices. So diodes are two-layer devices. Your LEDs are two layers. Rectifier diodes are two layers. Anything that's a diode is a two-layer device. Transistors are typically going to be three layers. Okay, this is our starting point. All right, so can we fill in the bottom of this? So pin 1 we decided would be emitter. And what type of material on the emitter? P-type. Okay. Pin 2 was base. And what type of material on the base? N-type material. And pin 3 is what terminal? Collector. And what type of material on the collector? Must be the same as the other outside pin, must be P. So you have deciphered through measurements which transistor is N-type and which transistor is P-type. Do we have confidence to be able to do this with a mystery transistor? Okay, okay, because all you have to do is identify a pin 1, 2, and a 3. Good. Let's go ahead and put this on pause.